In problem 2.3, we are told that we have the result that the mean of n, or the expected value of n, can be written as a sum of survival probabilities if n is a stochastic variable taking the value 0, 1, 2, 3, and so on. Now, what is the goal of problem 2.3? Well, the goal of problem 2.3 is to express the expected excess lifetime in a similar fashion using a sum of survival probabilities. So first of all, how should we interpret what goes on in this exercise? They say let n be a lifetime. So n denotes lifetime. So if a person lives until age 65 and dies at 65, then 65 is that person's lifetime. If another person dies at age 24, then that person's lifetime is 24. So since n is a value that we can determine in the future, if we're standing at time 0 with a newborn baby, then n as a lifetime is stochastic, which is why it will be interesting to find the mean of n. And then they say let d be an integer that is greater than or equal to 0. So d can attain values 0, 1, 2, 3, and so on and so on. Now we are asked to consider the expected excess lifetime. Expected excess lifetime, which is given as such. It is conditioned on the fact that a person survives age d. What is the expected value of the remaining number of years n minus d that the person has left? And we call this the expected excess lifetime. In Danish, we call it restlevetid. So the name kind of explains itself. So our goal in this exercise is to find an expression for the expected excess lifetime similar to that of E of n here. So find an expression for this similar to a sum of survival probabilities. Now, a good way to start is to take a look at the place where the exercise tells us it's got its inspiration from. So let's take a look at how the book shows that the expected value of n can be given as a sum of its survival probabilities. So this is a clip from the book. And now let's just try to figure out what goes on here. So the first equality sign just comes based off of the definition of mean value. This is the exact definition of expected value. It is the sum of each value that n can attain multiplied by the probability that n will attain that value. Now, for each value of n, what essentially happens here is we sum pn n times. And what do I mean by that? Well, 1 multiplied p1 is the first term, right? The second term is 2 multiplied by p2. The third term is 3 multiplied by p3. Now, what is that exactly? Well, actually, if we should write this as just one sum with no multiplication signs at all, then what's going on here is I have p1, and then I have plus 2p2. So that is plus p2 plus p2. So I have that twice. Then I have plus p3 plus p3 plus p3, because I have that multiplied by 3, and then plus p4 plus p4 plus p4 plus p4, and so on and so on. So what does that correspond to? Well, that corresponds to the fact that instead of writing n, I say that I look at the sum from 1 up to n, because then I can replace n with the symbolic notation for this thing over here instead, right? So if n is equal to 1, then this sum is just equal to 1. If n is equal to 2, then I will sum the number 1 twice, so 1, 2, and then I take 2 and multiply by p2, and so on. So this is based on the fact that n is equal to the sum of 1 n times. Now what I want to do is switch the summation signs. I want the outer summation sign to have index m and the inner summation sign to have index n. And the reason why I want that is because I want to be able to sum some of these probabilities together. Now, how can I do that? How can I go from the sum over n equals something over the sum of m equals something, and then change that to have an outer sum of m and an inner sum of n? Well, there are two ways we can do that. One is by using common sense. Another is by using indicator functions. They're kind of two sides of the same coin. So let's just take a look at how we do this using indicator functions. So with indicator functions, what we say is, instead of these bounds being in the sum, we move them inside an indicator function and just let the bounds be the loosest bounds, 1 to infinity. And since both bounds are just 1 to infinity, then there's nothing wrong with switching over. So here we move bound inside indicator. And then by the next equality sign, we switch order of summation. And upon switching the order of summation, we can think a little bit about, well, how can I move the indicator sign back up there? So now the indicator sign has some information that we will just plug back into the inner sum. And what we can see is, since we have that m is smaller than equal to n, we have that based on the indices for the inner sum here in the beginning. But since m is smaller than equal to n, that is equivalent to the fact that n is greater than equal to m, which means that n should have the values m, m plus 1, m plus 2, and so on and so on. So therefore, I can move the indicator function back up into the sum by saying that, well, all of the terms where n is strictly less than m, they just evaluate to 0 because of the indicator function. So that's the same as summing for n equal to m up to infinity. So what has happened essentially is we have switched the order of summation, and in doing so, we have also changed how the bounds look. And then in the last part here, we can see that if I sum Pn for n going from m to infinity, well, that is just the same as the probability that n is equal to m, plus the probability that n is equal to m plus 1, plus the probability that n is equal to m plus 2, and so on and so on. So all in all, it is the probability that n is greater than equal to m. And that's how we reach this conclusion. Now, if we should make a drawing of how we switch the summation signs, we're also able to do that. So let's just try to make a drawing here of how we can switch the summation signs. So the sum for n equal 1 to infinity over the sum of m equal 1 to n. We want to show that this sum is equal to the sum for 1 going to infinity with m in the outer sum here over the sum of n going from m to infinity over Pn. So how can we show this? Well, we can try to draw a grid. So let this be n and this be m. So what do we have here? Let me try to plug in some different values of n here. 1, 2, 3, 4, 5. When n is equal to 1, which values can m attain? Then m can be equal to 1 as well. So we sum Pn for m equal 1 and n equals 1. And then n is equal to 2. When n is equal to 2, which values can m attain? Well, then m can attain the values 1 and 2. Okay, for n equal to 3, which values can m attain? M can be 1, 2, 3, which means that we sum Pn for n equal to 3 and m equal to 1, and then for n equal to 3 and m equal to 2, and then n equal to 3 and m equal to 3, and so on and so on. So you can kind of see that this creates this triangular structure here. Now, if we should think about how we can express these wonky crosses here in terms of m first and n second, how could we do that? So for m equal to 1, which is this line here, what can n be equal to? Well, then n is equal to 1, 2, 3, 4, and so on. When m is equal to 2, then n is equal to 2, 3, 4, and so on. When m is equal to 3, then n has the smallest value 3, and then 4, 5, 6, and so on. So for each different value of m, n must be greater or equal to that value of m, which is why we can do this change in summation. So that was a little bit about how we found this result in the book. The reason why I wanted to talk about this is because, well, first of all, probably not all of you have understand what goes on in that section in the book. And second of all, because it's always good to take some inspiration and get some ideas from the book for your own proof. So it's quite probable that we will have to do a trick that reminds of this thing in our own calculations very soon.